So welcome to this session on line integrals. Here in today's class you will be learning about Gauss Divergence Theorem and how to apply it in problem solving. So what exactly is Gauss Divergence Theorem? If V is the volume bounded by a surface S and F is a continuously differentiable vector function, then triple integral over V, divergence of f dv, will be double integral over S f dot n ds, where n cap is the outward drawn unit normal. So we are basically connecting triple integral with double integral here. So we'll just be working out a few problems on this, and the problems are lengthy, mind you. So moving on to the first problem, if f equal to 2x squared minus 3xzi minus 2xyj minus 4xk, evaluate triple integral over V, divergence of f dv, where V is the region bounded by the plane x equal to 0, y equal to 0, z equal to 0 and 2x plus 2y plus z equal to 4. So first of all, how do you calculate divergence of f? So divergence of f is del by del x of the x coordinate plus y del by del y of the y coordinate plus del by del z of the z coordinate. So in this case you will get del by del x of 2x squared minus 3z, which is 4x, then you get minus 2x and that's it, which is 0. So you get 4x minus 2x, which is 2x. So applying the formula, triple integral over V, divergence of f dv will be double integral over S, 2x dx dy dz. This is the divergence of f. And you are integrating over z equal to 0 to 2x minus 2, 4 minus 2x minus 2y. Now if z equal to 0, y will be 0 to 4 minus 2x divided by 2, which is 2 minus x, and if y and z are both 0, x will be 0 to 2. So this is how we write the limits. And now integrating, we start with the integral of z. So you get integral of this will be 2xz within the limit z equal to 0 to 4 minus 2x minus 2y. That will be 2x into 4 minus 2x minus 2y. The rest of the integrals remain the same. And that will be twice integral x equal to 0 to 2, y equal to 0 to 2 minus x. When you multiply, you get 4x minus 2x squared minus 2xy dy dx. Take out the 2 here. And this will be 2, when you integrate with respect to y, you get 4xy minus 2x squared y minus 2xy squared by 2 within the limits y equal to 0 to 2 minus x. I'm actually explaining the integration. So this will be integral x equal to 0 to 2, 4x into 2 minus x minus 2x squared into 2 minus x into 2 minus x the whole squared dx. So that would give you 8x minus 4x squared minus 4x squared plus 2x cubed minus x into, when you expand this you get 4 minus 4x plus x squared. Opening the bracket you get 8x minus 4x squared minus 4x squared plus 2x cubed minus x into 4 minus 4x plus x squared. So you get 8x minus 4x squared minus, that is 8x minus 8x squared plus 2x cubed minus 4x plus 4x squared minus x cubed. So when you simplify, this will reduce to 8x minus 4x, which is 4x, minus 2x squared plus 4x squared, which is minus 4x squared, and plus 2x cubed minus x cubed, which is plus x cubed. Again integrating with respect to x, you get 2 4x squared by 2 minus 4x cubed by 3 plus x raised to 4 by 4 within the limit 0 to 2. Substituting within the limits, you get the final answer as 8 by 3. Okay, coming to the next question. Use divergence theorem to evaluate double integral over S f dot n ds over the entire surface of the region bounded over the xy plane bounded by the cone z squared equal to x squared plus y squared, the plane z equal to 4, and f is given by 4xz plus xyz squared j plus 3zx zk. Now by Gauss's divergence theorem, you know that double integral over S f dot n ds is triple integral over V, divergence of f dv. So divergence of f will be partial derivative with respect to x of 4xz is 4z plus partial derivative with respect to y of this is xz squared and partial derivative with respect to z of 3z is 3. Now if you put z equal to 4 in z squared equal to x squared plus y squared, we get x squared plus y squared equal to 16. So your integral reduces to triple integral over v divergence of f dv, that is integral z equal to 0 to 4. Now this is a circle. So the limits will be x varying from minus 4 to 4, y going from minus root 16 minus x squared to root 16 minus x squared, 4z plus xz squared plus 3, dy, dz, dx, dz. So this would be when you integrate with respect to the function of y is even, so it will be 4z plus xz squared plus 3 within the limits z equal to 0 to 4, x equal to minus 4 to 4, and this is 0 to root 16 minus x squared because the function in y is even. And now integrating, you get this as 4z plus xz squared plus 3z within the limit 0 to root 16 minus x squared, which is root 16 minus x squared. You're integrating with respect to y and dx dz. So this will be integral twice integral z equal to 0 to 4, x equal to minus 4 to 4, 4z into root 16 minus x squared plus 2 into z squared xz squared root 16 minus x squared. The limits remain the same, plus 2 into 3, 6 into integral over z integral over x root 16 minus x squared dx dz. Now this is an odd function of x because the term in x is 1, so this becomes 0. You have the rule integral minus a to a fx dx is 0 if f is even, and equal to twice integral 0 to af if f is even. If it is 0, it is odd. So this becomes, for when you take out, you get, becomes integral 2 into 4, 8, 8 into 2, 16. Z equal to 0 to 4, x equal to 0 to 4, z root 16 minus x squared dx dz, plus 2 into, when you integrate this, you get root 0 to 4, root 16 minus x squared. So you get 2 into 6, that is 12, z equal to 0 to 4, x equal to 0 to 4, root 16 minus x squared dx dz. Note that this integral becomes 0. Now we have the formula integral root a squared minus x squared dx is x by 2 root a squared minus x squared plus a squared by 2 sine inverse x by a. So this becomes 16. Z, you're integrating with respect to x, so z remains outside. X by 2 root 16 minus x squared plus a squared by 2, which is 8 sine inverse x by 4 within the limits x equal to 0 to 4 dz. And the same thing applies here. 12 integral z equal to 0 to 4. We have the same thing within the limits x equal to 0 to 4. So substituting, you will get, when you substitute within the limit z equal to 0 to 4, this becomes 0. You get 8 sine inverse 1. And this becomes 12 sine inverse 12 into 8 sine inverse 1. And then you know that sine inverse 1 is pi by 2. So this is 16 integral z equal to 0 to 4 z into 8 pi by 2 plus 12 integral z equal to 0 to 4 8 into pi by 2. So finally substituting, you will get it as 704 pi. So that comes to the end of Gauss's Divergence Theorem Part 1. There's a lot of heavy integration here, and I hope I have helped to make it easy for you. Thank you and stay tuned.